Hello calculus students, here we are with a 4.4, the chain rule, which is a way to greatly increase the variety of functions that you can actually take a derivative of. Because basically you break it up into parts. The chain rule is designed to deal with things like this on the right here. See how these are compositions of functions. There's an x squared plus 1 inside a square root. Here's a 3x plus 2 inside a fifth power. Here's the cube root of x plus 2. Here we don't need the chain rule. We can just distribute the derivative over addition. But the derivative does not distribute over composition of functions. That's where we have to be careful. And so here, we're going to look at this problem involving a gear chain. Here's a set of gears, such that the second and third gears are on the same axle, this axle right here. And as the first axle resolves, it drives the second, which then turns the third. So, as we're turning these, as this one turns clockwise, this one will turn counterclockwise. But not nearly as fast though, because this is smaller. That'll also turn this one, and then it'll turn gear 4 like this. But what we're going to look at now is, since this is in a 3-to-1 ratio, this will go a third as slow, right? And this one will go, since the radiuses are in a 1-to-2 ratio, as this spins once, this will only spin around half a time. So this is half as fast in terms of its spinning. But let's look at dy with respect to u. If y is the revolutions per minute of axle 1, and u is the revolutions per minute of axle 2, and x is the revolutions per minute of axle 3, then dy du is the rate of change of y with respect to u. And y is going to have to spin twice as fast because it's half the size, half the circumference. So that's why dy du equals 2. And du dx, look at these two axles now here, the x axle and the u axle. Because the gear connection right here, this u is going to have to spin twice as fast to catch up with gear 4. I'm sorry, I meant 3 times as fast with dy du. And du dx is 2. So therefore, the y axle will turn 6 times as fast as the axle 3. And that's what we see in their solution. So, this is the idea of how the chain rule works. dy du times du dx cancels this out, where u is this sort of intermediate function between two things. Here's the chain rule in practice. Y equals f of u, and u in turn is g of x. So here's our composition idea. Y equals f of g of x. So you can take the derivative by taking the derivative of the outermost function first, and then multiplying by the derivative of the inner function. Here it is in what we call the Leibniz notation, and here it is in the functional notation, f prime of g of x. Notice how we're leaving the g of x alone. And then take the derivative of the inner function. So a nice diagram here, and I've also expressed it here in just plain old English. Take the derivative of the outer function whilst leaving the inner function alone. See this over here? Leaving that alone. And then in another step, multiply by the derivative of the inner function. So that's what we're doing here. That's the ideas behind the chain rule. Let's practice using them. First we'll explore the old way and the new way. The old way on this one, if we call this f of x, the old way would be quotient rule. And you say, oh well, to do the derivative, we got to take the bottom times the derivative of the top, which is 0, minus the top times the bottom, which is 3, all over the bottom squared. So we get negative 6 over 3x plus 1 squared. Whew. The new rule says first, rearrange it. We can write it like this. We can say, first of all, f of x equals twice 3x plus 1 to the negative 1 power. And now, we can use the chain rule. That is, our outer function is this negative 1. The 2 is just a constant multiplier, comes along for the ride. But the negative 1 comes down in front, and we take 3x plus 1 to the negative 2 power. Whilst leaving the inner function 3x plus 1 alone. But don't forget this step now, to multiply by the derivative of the inner function. The derivative of 3x plus 1 is 3. And so you can see we get negative 6 times 3x plus 1 to the negative 2, which is the same as what we have over there. This would be a fine answer like this. Okay? Let's try another example. The old way would be to say, oh, we can't do this because we can't distribute derivatives over this composition. So the old way would be to go through all the hassle of first expanding it out, saying f of x is x cubed plus 3 times x squared times 2 plus 3 times x times 2 squared plus 2 cubed. And so we simplify it down to x cubed plus 6x squared plus 12x plus 8. Now you can take the derivative. So this was still, let me just make sure you're clear on this. That's still just the original function. Now we're doing the derivative, and we get 3x squared plus 12x plus 12, because we can distribute the derivative idea over addition. Now the chain rule way, we can dive right into taking the derivative. It's ready. We can say 3 times the inner function raised to the second. That's taking the derivative of the outer function, the cubing. 3 times yada yada squared. But leave the inner function alone, x plus 2, and take another step to take the derivative of the inner function. In this case, it's just plain old 1. So we get for the derivative 3 times x plus 2 squared, and that's just fine. I'd like to make sure that we've got the same function each here. That's x squared plus 4x plus 4, and we distribute the 3, you get that. So they do agree. But you can see how the chain rule much easier in this case. Here in this first case is about the same, only because you had a very sort of quotient rule with an easy derivative up top here. But see how it's easier to write it like that. Okay, so to use a chain rule, you have to decompose functions. And so here we're just illustrating some ways of thinking of something like 1 over x plus 1 as a composition of two functions. X plus 1 is the inner function in this case. And here y equals the square root of 3x squared minus x plus 1. This inside of the radical, 3x squared minus x plus 1, is the inner function. Now use the chain rule. Here's a good example of an inner function. U equals x squared plus 1. That's our inner function. And the derivative of u with respect to x then is just plain old 2x. So you don't have to write that down. I was just helping to illustrate what the inner function is. And so when we start doing the derivative on this, y prime will be 3 times yada yada squared. That is, I'm just taking the derivative of the cubing right now. And then I look at the inner function as x squared plus 1, and now I have to multiply by the derivative of that inner function, which is 2x. So we get 6x times x squared plus 1 squared. No need to expand that out. In fact, we like it in a fully factored form like this to help discover roots. We could have also done 3 the old way, expanding it and then taking the derivative. But, that would have been a little more work. And look at something like this. Which would you use on x squared plus 1 to the 50th? Do you want to expand it all, or do you want to use a chain rule? Well, chain rule, of course. Because with the chain rule, you get 50 times x squared plus 1 to the 49th, and then you just have to multiply by the derivative of the inner function, 20x. And so you get 100x times x squared plus 1 to the 49th. So much easier than actually expanding out, taking the 50th row of Pascal's triangle. Could you imagine? That would be a triple Pippin problem, if you really want to do all that work. Okay. Now the general power rule just applies the chain rule to powers of what we just did here, a function. Instead of just x to the n, now it's some function of x raised to the n. Okay? So, let's apply in this case, find the derivative. So f prime of x, this one's ready to go. We can say 3 times, leave the inner function alone, 3x minus 2x squared raised to the second. And now take the derivative of the inner function, which is 3 minus 4x. And this is fine. The original answer is fine. I usually, if this was a number, I'd combine it with the other number, but we can leave it like this. Now, it might help us to, in fact, when we're looking for roots, to say, oh, but we can take an x out of this, leaving behind 3 minus 2x. Both those are going to get squared. So we actually get 3 times 3 minus 4x times x squared times 3 minus 2x squared. And there'll be some advantages in leaving it in that form, but I would not have docked you if you had left it like that. Okay, what happens when we have radicals? Find all the points in the graph of the cube root of x squared minus 1 squared for which f prime of x equals 0 for those which the derivative does not exist. Well, what we might want to do is first take the time to rewrite the function as x squared minus 1 to the 2/3 power. That can really simplify things. Now we can go to the general power rule and take the derivative. It also helps, I color code it, but you should do this when you're doing a problem. Let me know when you're actually taking the derivative, as opposed to maybe you want to change the form of the function to make it be an easier derivative. So we get 2/3 x squared minus 1 to the 2/3 minus 1, and then we need that derivative of the inner function, which is 2x. So I'm getting 4x over 3 times x squared minus 1 to the negative 1/3, which actually makes 4x over 3 times x squared minus 1 to the 1/3 power. So we might want to look at this and say, well, when is the derivative equal to 0? That'll be when the numerator equals 0, or 4x equals 0, so at x equals 0. So at x equals 0, f prime of x equals 0. Now, when is the derivative undefined? That's when the denominator will equal 0 in a fractional expression like this. So we take 3 times x squared minus 1 to the 1/3 equal to 0. Divide by 3. Raise both sides to the third. You get x squared minus 1 equals 0, so x squared equals 1. So x equals plus or minus 1. At x equals plus or minus 1, the derivative is undefined. And we can see that in the graphs. Here's the original function, cube root of x squared minus 1 squared. And notice those sharp corners there that happen at 1 and negative 1. Well, the directional derivatives won't agree. And in fact, we get, for the derivative, an undefined slope. So the derivative is undefined at 1 and negative 1. Right here, though, at x equals 0, we have a horizontal tangent line. So the derivative is equal to 0 there. And that's the only time we get a 0 slope. Now, we've seen this problem before. Differentiating quotient with constant numerators. If this is a constant, you don't really need the quotient rule. It behooves you to just change the form a little bit and say this is negative 7 times 2t minus 3 squared. And now we can just use the constant multiplier rule to say this is negative 7 times 2 times 2t minus 3 to the first, and then don't forget the derivative of that inner function, which is 2. And so we get negative 7 times 2 is negative 28 times 2t minus 3. And that's the derivative. Much easier than going through all that hassle of the quotient rule. That's what's pointed out in this note right here. Generally, it's much more efficient if you can avoid the quotient rule. So how do you know when you don't have to use the quotient rule? Well, look to see where the unknowns are. If you have unknowns in both the top and the bottom, and there's no easy way to just take the bottom as a monomial and divide it in, then go ahead and use the quotient rule if you have unknowns in the top and the bottom. Now, simplifying derivatives. Now, I'm going to give you most of the credit problem for doing the raw derivatives, and I'm going to let you use your T99 to simplify it further. For instance, in this case, this ends up being a huge mess when you take the product rule on this. Here's the original function. We rewrote a little bit, and the product rule. Notice you leave the x squared alone, take the derivative of the other function, and then leave the other function, 1 minus x squared to the half alone, and then take the derivative of x squared. And this can be a lot of tedious algebra. So, like in a 10-point problem, you would get 8 points for showing me this step. After that point, you could use your calculator to simplify out and so forth. Or do it by hand for another 2 points there. Now, they mentioned that you can also simplify these by rationalizing, dividing out something that will rationalize the numerator. So, for instance, in this case, we've got this big mess here. Maybe if we factored on next to the half, it would work out simpler, and it does. Now, the derivative of a quotient, again, we have to use quotient rule on this, and it gets to be a huge mess. But again, this would give you most of the points here, applying the quotient rule correctly. Now, simplifying the derivative of power. Notice in this case, you've got a function raised to the 2, so your outer function is the squaring. So the general power rule, which is essentially the chain rule, applies first. Bring the 2 down in front. Leave the inner function alone. It's only raised to the first now. And then take the derivative of the inner function. And that's where a lot of your work is, because you have to use the quotient rule on that. And then simplifying out, you get this answer. Here's our derivatives rule so far. The constant multiplier rule. Notice how that's different than the product rule. If c is a constant, you just bring along for the ride. But if you've got two functions in x, you've got to go through the product rule. Derivative of a constant by itself is 0. The chain rule we just talked about, and as it applies to the general power rule. The power rule is one of the key ones. Derivative of x to the n is n times x to the n minus 1. There's your quotient rule. And you can distribute the idea of derivative over addition and subtraction. This is certainly something you could have on your formula sheet, and you might want to have it as part of your exam prep. Okay, here's another example of the chain rule, because we got a function 1 over t minus 3 inside a squaring function. So I'm going to use chain rule. So for the derivative, and I don't think there's much point in expanding this out. For the derivative, we get, oh, hold it. I just had a brainstorm here, people. Remember what we talked about with the constant in there? Let's just hold the bus. Hold the bus. We could rewrite the original form and write this as t minus 3 to the negative 1 power, all raised to the 2. So the original function is t minus 3 to the negative 2 power. Now we can flip over to the derivative much easier using the chain rule. Negative 2 times t minus 3 to the negative 2 minus 1 times the derivative of the inner function. In this case, it's just 1. So we get negative 2 times t minus 3 to the negative 3 power. And that's fine for a final answer. Some people like to put it in sort of the form of the original question. There were no negative exponents, so they'd write it like this. And now we can see we're going to have an undefined derivative at t equals 3. Now, there's one more I want to look at, and that's with second derivatives. Evaluate the second derivative of the function and use a computer algebra system to verify your results. So I'll show you how you can do this on your TI 89. Again, this one I would think we'd want to rewrite the form. If we write the form as f of x equals 1 over x plus 4 to the half, and that becomes x plus 4 to the negative a half, now it's much easier just to apply the chain rule. Prime of x is negative a half x plus 4 to the negative a half minus 1 times the derivative of the inner function, and that's just 1. So we get for the derivative negative a half x plus 4 to the negative 3 halves. And now, since we're looking for the second derivative, this is great form for the second derivative too now. Now we can say, for the second derivative, we can bring the negative half along for the right, it's a constant multiplier, times negative 3 halves, bring the power down in front, x plus 4 to the negative 3 halves minus 1, and then multiply by the derivative of the inner function, and that's still 1. So we get for the second derivative 3/4 x plus 4 to the negative 5 halves power. And it says put it in when x equals 0. So we're looking at the point 0 a half. So f double prime of 0, the second derivative at 0, is 3/4 0 plus 4 to the negative 5 halves. So we get 3/4 times 4 to the negative 3 halves, and you can pop that in your calculator. I'm going to try to do it by hand here. We get 3/4 times 2 squared to the negative 3 halves. So that's 3/4 times 2 to the negative 3. And so we get 3/4 times 1 over 2 cubed, or 3 over 8 times 4 is 32, 3/32. Let's see if the TI-89 agrees with me. Now here's what you need to do on your TI-89 to do a second derivative. You get the little d command out, and then it's 1 over the square root of x plus 4 at x equals 0 comma half. So derivative of 1 divided by square root x plus 4 with respect to x, so you have to comma x, comma 2, and that's for doing the second derivative. Now if you just do that much, let's see what happens. My calculator says 3 over 4x plus 4 to the 5 halves. And that's consistent with what we have over here. And for our next step then, that really doesn't answer the question though. It asks for what's the derivative of x equals 0. So you just take one more step. And I'm going to try that on the calculator. That is, you take the derivative of 1 divided by square root of x plus 4 with respect to x, and 2 stands for second derivative again. And then you can put with x equals 0. Okay, so let's just add those commands on. With x equals 0, and my calculator says 3 over 128, which means that I probably erred. Let's find out where I made a mistake. Yeah, this is a negative 5. Negative 5. Negative 5. That's why it's good to check things on your calculator too. The negative 5. And so we get 1 over 2 to the 5th over here. And 4 times 32, sure enough, is 128. Over 128. And now both answers jibe. Flange out.